Hi, I'm your favorite Daryl Sinclair. I'm about to revolutionize 3D printing by giving people the option of using either plastic filament deposition or using continuous wire feed metal deposition. Now, I'll give you a little history on myself. In 1981 I became a welder and did that for a while, and then went back to school and took computing sciences and became a computer programmer systems analyst. And subsequent to that, I went to work for a company and married the two disciplines together by becoming a robotic welding technician. Now, today is January 22nd, 2014, and on this date last year, I was totally clueless about 3D printing. I had no idea what it was, and I had heard a lot of news and hoopla about it, but dismissed it, thinking it was just, you know, somebody's got their HP desktop printer and they're printing something that's 3D, like a picture or something. I had no idea that this whole concept of 3D printing. So in about April, I went out to YouTube and did some research on 3D printing, and lo and behold, I was amazed. Really, frankly, my mind was blown. I had no idea that people were actually building objects with this 3D printing. So with my mind and my experience and knowledge, I went to work working on metal deposition. And I looked into different types of metal deposition and what have you, like the laser sintering, and they have the cladding where they use the spray powder into a weld deposit. And nothing seemed to work for a desktop or kitchen table build. I should say from the outset that this is going to be a 3D, or I mean open source system. I'll be uploading all the videos and drawings and what have you onto RepRap, and so to me this is too important to be kept under a patent by any one man or group or company. This has to get out to the public, and this is the venue that I think is right for doing it. So going back to my concept, now this goes back many years. I attended for briefly the Northern Alberta Institute of Technology, and in one of the courses the instructor put forward a question. He asked, how do you direct radiation at a cancer cell, burn out the cancer cell but not damage any of the tissue around it? And the class was stumped, but he went on to explain, so you don't use one beam of radiation, you use an array of beams. And he said each beam in itself does not have the power, you don't have the power to damage any tissue, but where they're targeted, at that point where they collide, the radiation is so intense that it burns out the cancer cell without damaging any tissue around it. So anyway, this was tucked in the back of my mind until about June of last year, when my ideas for metal deposition all came together. Now, instead of using arc welding, which is quite impossible. Now, I should bring up this other little thing. I subscribe to an e-magazine called Gizmag, and on December 3rd of last year, I received an email with them, and there was a photograph in there that really caught my eye because it was about welding. And the article was titled, "Low-cost open source 3D printer looks beyond plastic." And the subtitle here says, "The metal 3D printer built by a team from Michigan Technological University for under $1,500. And they show this picture, and they've since uploaded their stuff to RepRap, where you can look at this picture, as well as they have an 8-page what do you call, paper on wire feed metal deposition. Now, you see all the sparks and the spatter happening from this. This is typical of MIG welding. And the problem is that you can't build that on your kitchen table, or you're going to burn your house down, okay? That is fine in a shop environment, but certainly not for your kitchen table. And that's what I want to have happen. I want to see this happen, that every person that is into 3D printing can build this system on their kitchen table and operate it there as well. So anyway, in the photograph here, what you see a pedestal that the wire feed is attached to, and what it's doing, it's sending the wire down, and it's really just MIG welding. Okay, now my concept is not to use arc welding, but to use an array of lasers. Hence the idea that was in the back of my mind for so many years. Now, one thing we have to think about is there has to be multiple lasers, because we want to heat the wire uniformly, okay? Meaning there has to be at least 2 lasers opposing and focused exactly opposite each other, okay? Now, my system calls for 3 sets of 2 lasers, okay? The top one preheats the wire before it's melted. The second set melts the wire, and the third set melts a puddle in the base that the wire can simply drip into. Now, what we're doing is not, firstly, we're not using an arc, okay? This arc that's in this photograph here, as soon as you strike that arc, it's an instant 3,000 degrees. Now, when that happens, it's instantly melting the material, and it's exploding out, and that's what the spatter and sparks is all about. It's the material being blown out, and you can't have that in this system. So the answer is lasers, okay? Because that's light energy, it's not electrical energy. So anyway, what we're doing with my system is mimicking gas welding, okay? And let me explain like this. A welder, if he's going to weld together 2 pieces of tubing or piping or whatever, what he will do, he'll have a nice blue flame on the end of his welding torch, and that flame is 3,000 degrees as well. But the difference is he's melting the metal. He'll manipulate that flame on the base metal until the base metal turns molten, and then he'll feed in what's called a filler rod into that weld, and he'll drip and drip and drip the metal into molten metal, okay? And that way he's controlling the temperature, and he's also with this, there's no smoke, or very little, and there's no arcing of any sort, okay? Because he's manipulating the heat when he's moving the welding tip, the torch. So with the laser system, we're doing the same thing, or very similar, okay? So something that I have to mention, this here, this is a printer bought hot end, and there's a resistor inside, okay? Now this, if it were in proximity to this metal deposition system, that metal is being melted. Mild steel melts at 2,500 degrees Fahrenheit, or 1,350 degrees centigrade. If this is in proximity to that kind of temperature, what happens is gradually the build is going to increase in heat until it's well in excess of what this can stand. So the drive for the wire feed is going to have to be remote, just like it is for this this welding torch. Okay. Now, problem with the drive on that, on a welder, if you're going to butcher a welder, you're going to have to change a motor, because the motor that's in a typical welder is an analog, and it doesn't lend itself well to being controlled digitally. Okay, it can't. So what you have to do is change out the motor and put in a step motor like is on the plastic filament deposition system. So now I'm gonna try to understand. I have to try to make this video 5 meg. Okay, so I can't go into all the details of everything. All I can do here is give you the base concept and the project, and I will be making videos on the how-tos and how to build your own system. That I will be putting those videos onto DVD, and they're going to become part of the rewards. And all I can give you here is the basics. We can't go into other types of metal deposition. We can't go into safety issues like goggles and all that. This is really just the basics, okay? Now, what I have here is another printer bot, okay? You don't have to use printer bot, okay? On RepRap there's probably 6 or more controller boards, Arduinos that will work, okay? Because essentially one thing that was controlling one part of the system with plastic deposition, there's simply a transition over to a different material, okay? And so the board itself will have to be isolated from the 3D printer itself as well, because again, because of the heat, okay? This will probably fry if it's within a foot of the build, whatever build you're doing. So anyway, this is a four-axis system. I'm trying to do this without damaging it. There's the XYZ axis and the E axis, and just like on the little extruder, the hot end there, the motor that's on that is just over to the wire feed, and this E-axis would control the same type of motor on the wire feed. So essentially you're doing all the same things, okay? Now when it comes to these two MOSFETs here, these two MOSFETs are what run the heat bed. On the plastic deposition, you have the heated bed where so that the plastic won't warp, okay? Don't need that in metal deposition, okay? The other one is controlling the resistor that's inside the hot end, and we don't need that either. So what's going to be happening is I'm going to be using these two heater connections for the lasers, okay? Now, the bottom two lasers, the ones that are forming the puddle at the base, will be run off of one MOSFET. The other 4 lasers will be run off of the second MOSFET. And why that's important, when the wire is coming in, it's cold when it comes out of the wire feed, and as it passes the first set of lasers, it's being preheated to about 2400 degrees, just below the melting temperature. As it comes down, it's being heated again by the second set of lasers to melting, to where now it's going to drip into the weld puddle. The third set of lasers are what forms the weld puddle, and so the liquid metal is dropping into liquid metal. Now what has to happen in the system is that this puddle has to start, it has to be formed before the wire starts hitting it, okay, or being added into it. And perhaps 1 second before the wire starts coming down, this puddle will be formed by the first MOSFET turning on, okay? The first and second sets of lasers will turn on slightly after the bottom one, okay? And what that does is it essentially mimics the gas welding process, okay? By having molten metal dropping into molten metal, as opposed to instantly turning everything into 3,000 degrees and blowing everything all over the place. Laser light won't do that. Now we have to talk about lasers briefly. Lasers are funny little creatures, okay? They will consume as much power as you give them, and so there's two ways to control the heat of a laser. One is by the amount of power going into them, and the laser diodes, they will consume as much power as they can until they burn out. So you put, just before that power hits the laser, you have what is known as drivers. And those drivers are controlled by what's called an LM317, plus there will be resistors as well. And now there's going to be a variable resistor that allows you to control the amount of power going into the laser, depending on what kind of metal it is that you're putting through the system. So if, for instance, you're building something out of titanium, you're going to need a much stronger power source, or more power going into the laser or coming out of the laser. So more power is required. So you turn down the resistance. Now that's one way of controlling the amount of heat coming out of the laser. The other way is, if you have a laser with, say for instance, a 1/2 inch beam, and that beam is 50 degrees at the lens, okay? If it continues on at a 1/2 inch or 12 millimeters in diameter, pardon me, and 50 feet away from the lens, it's still going to be 50 degrees, okay? But what you do is you focus down that laser beam down to a very fine point where it converges. It can be as much as 10,000 degrees. So this is what we're doing with the lasers in the system, is we're focusing them down to approximately 1 millimeter, and at 1 millimeter they're going to have exponentially more power than what's at the lens. So say for instance we have a 5 millimeter beam at the lens that's, say, 100 degrees at the lens. When it's focused down, it can be 10,000 degrees at the point where it's focused, okay? And that's the second way of controlling the lasers. So this whole system will be coming together very quickly, and to that end, I need your support, and I'm looking forward to working with everybody and get this out to the public as soon as possible, and hope nobody tries killing me in the meantime. But yeah, so I hope you see there's an air of urgency involved in this, and to get this out to the public as soon as possible, and I hope you're behind me, and I look forward to getting out all the rewards and everything else, okay? Thank you very much for watching, and we'll see you in the future, or we'll see you in the pasture, okay? Okay, thanks a lot. Bye-bye.